I, I welcome you again uh, in my next next lecture, and in this video I'll be talking about the implications of the models basically that we have discussed, like uh, we talked about Sommerfeld model, and we discussed the theory of this model in the context of quantum mechanics, and we chose two domains. One was the particle in a one-dimensional system, and we extended the one-dimensionality of the problem into three dimensions. And we tried to understand the basic definitions of metals uh, in the framework of metals, that how the density of the states behave in the core of the context. So the point is that when you do science with curiosity. It's all about curiosity. What if? What if? And this small phrase, what if, has led us to the current world filled with smartphones and technologies around us. And the growth has gone exponential. We find all those small questions into a range of technologies available in the modern world. Now, what is my intuition in this video is basically I would like to talk about quantum wells, and I believe that we have developed uh, a, a basis for understanding the real materials, the real nanomaterials. And as we know what is a nanomaterial, if while synthesizing a material, you restrict the dimensions of your material to the nanoscale. So typically talking about the nanoscale is between 1 nanometer to 100 nanometers. So we have nanoscale, and we can do it in the laboratory. We can synthesize our materials in which uh, either one dimension is at nanoscale, the other two dimensions are at the lower scale, or all the three dimensions are at the nanoscale, and vice versa. So this will lead us to a range of nanosystems. You will have one-dimensional nanosystem, two-dimensional nanosystem, and you will have three-dimensional nanosystem. Now, what is grossly important here for us to understand is the Sommerfeld model that we used for metals. The very core assumption was that the electrons living in those systems will never see the boundaries. And we solved Schrodinger's wave equation in that context, and we could obtain some of the important physical quantities that could be related to these metallic systems. And some of them were Fermi energy, Fermi level, Fermi sphere, when you talk about a three-dimensional box, and then using those basic definitions, we could finally achieve the very important parameter of those systems, what was called as density of states. But what was extremely important in that context was that the electron will never see the boundary. The electrons, you have a range of electrons living in the Fermi surface at absolute zero, and these electrons will never see the boundary of that metal. Now, such class of materials are called as bulk materials. So if I have a wire of copper, it's a bulk material. A wire of gold, it's a bulk material. So that context for us was that we were trying to realize those systems in the framework of bulk systems. But we have to talk about the nanosystems, and we have to extend our basic understanding into these nanosystems. And we would certainly be interested in realizing the behavior of density of states in these nanosystems. Now, today's topic, as you can see, is the quantum well in the nanomaterials. Now, the point is that what is it when you design something? What is it that you call as quantum well? Now, if you have a three-dimensional system in which two dimensions are macroscopic, I mean, what I said before, they possess the dimensions of the bulk material. I have a 3D object, say X, Y, and Z. Now, if X is ordinating the dimensions of a bulk system, the Y is ordinating the dimensions of the bulk system, but the Z axis of this material are falling in the context of nano dimensions. That means if I assume that the Z of my material that I'm talking about, this Z is nano in size. So nano, we understand, a billionth of a meter. So it's a very, very thin layer. The other two dimensions are macroscopic dimensions. These are big dimensions. These are bulk dimensions. Now, if I assume this material with two dimensions macroscopic in nature and the third dimension nano in nature, then this material is what's called as quantum well. This is probably the basic definition, the basic argument of what a quantum well is. So we would like to discuss this quantum well. So certainly it has to do a lot with the nanomaterials which we are designing in our laboratories, synthesizing them, designing them, characterizing them, and looking for their density of states, looking for their properties, transport properties, and so many things. Now, to introduce you with the quantum well, you can see what a quantum well is, basically, if you think it at a very, very basic level. So quantum wells are potential wells that confine particles. So you have the confinement of the particles, such as electrons in one dimension. As I was saying you, X, Y, and Z. So you are confining the Z. The Z dimension is confined at the nanoscale, allowing the motion in the other two dimensions. So that is electrons, they have a probable motion along X and Y, which are macroscopic in dimensions, but their motion is confined along the Z direction. So what happens? This leads to the quantization of energy levels. So along Z, there is quantization of energy levels. You have discrete energy levels of the electrons. But thinking about the energies of these electrons along X and Y, these energies are continuous energies. These are the energies that are very linked with the bulk systems. So they are fundamental components in nanomaterials and quantum devices like lasers and detectors. Now, lasers and detectors is not the only thing. There are a range of other devices where we design these quantum wells to obtain our devices with the properties that we are interested in. with the characteristics that we are interested in, so that these devices can be employed in our technology for either raising the efficiency of the solar energy or any other technological implications. Now, thinking about it, now how we can practically think about a quantum well structure. I mean, how can we have an idea of designing a quantum well structure in the laboratory? A quantum well is typically created by sandwiching a thin layer. We take a thin layer and what we do of low band gap. And low is the Z that I was talking about, semiconductor between the two layers of higher band gap materials. So what you do, you sandwich a very, very thin layer of the material by the two semiconductors of whose band gaps are large. Now, this heterostructure confines carriers in the thin layer because there is the difference in the band gap, and so what's happening here is the charge carriers they are prompted, they are confined to be in this thin layer and forming the discrete energy states. So what you are doing is you are generating the discrete energy states for these electrons, because these electrons are living in a very, very low dimensional system, and at least the energy of these electrons along the z direction are quantized. Then, so what is important for us in this video is to basically understand the density of states of these quantum wells, which are basically the property of these materials. So what we will see when we will discuss the theory of these quantum wells, we will come across the density of states. The density of states for these quantum wells as equal to m star by pi h bar square. I will not choose m star because m star is basically because the electrons are living in an environment of interactions. The electrons are living inside the lattices, and there are electrostatic interactions happening with the electrons. So the mass of the electron is not the pure identical mass of the electron that we always use. So here we will have the effective mass of the electron. That's why we have put down m star. But in my discussion, I will not be writing down m star. I'll be writing down m. But it should be taken to your understanding that this m star is the effective mass of the electron. So m star is the effective mass of the electron, and h cross is your reduced Planck's constant. And then, so we'll try to breach the idea of the density of the states for these quantum wells, and then we will try to talk about the total energy, because the total energy will certainly be a compromise of the energy along x and y and the energy along the z. So here we will see that this E of n that's written over here, this is already understood in the domain of quantum mechanics, that we will have discrete energy levels, and this k is the wave vector in the plane that we have the next term, and this m star is the effective mass that I have talked about. And when we will develop this mathematical state for these quantum wells, we will certainly come across the two results. These two results will be obtained. One is because your nanomaterial is purely its dimensions are equivalent to a particle in a box along z direction. So what we will see is that this electron will have discrete energy levels along the z-axis, but talking about its energies as a combination of x and y, we will have the continuous form of energies. And then talking about the density of states, we will see that the density of states will be independent of the energy, and we will have a step-like density states for these quantum wells. And you can see the constancy of, you have the density of states, and then there is a jump, then you have constant density of states, then you have a jump, and then again you have a constant density of states. Because in fact you will see that density of states will be independent of the energy. So this was the introduction of the topic that we would like to discuss. Now let's go into the mathematical treatment of this problem. So what we have is we have a quantum well, and for the quantum well we have a quantum well. So as I said, I talked about the quantum well. What we have is we have x and we have y and we have z. But x is macroscopic, y is macroscopic, and z is nanosize. So you have a problem in which electrons have macroscopical liberty along x and y, but its liberty is constrained along the z direction. This is my problem. So this is basically the basis of my quantum well. So when you design a nanomaterial in the framework of quantum well, what is essential is your x and y have to be macroscopic and z has to be in the nanoscale range. So first, looking at x and y, and we can immediately think about Schrödinger's equation for these two domains, for these two dimensions, which are macroscopic dimensions. And then we can immediately think about the z direction, and in the z direction, the size of your system is equivalent to the size of a nanometer. So for x, y, what I will have Schrödinger's equation d2 psi by dx2 plus 2m by a cross square e minus v of x of psi equals 0. Now, as I said, that we are intrinsically using the Sommerfeld model here to understand the properties of these nanomaterials. So the potential of this electron within this nanomaterial is assumed to be 0. So 0 is a constant. So this equation will boil down to d2 psi by dx2 plus 2m by a cross square e of psi. So this is my macroscopic, I may call it a macroscopic Schrödinger's equation, because the dimension of my material is large. So along x, my material is acting as a bulk material. So its properties are not going to change at some particular temperature. So if it is gold along x, it is gold along x every time. But, so the same story will go along y. So along y, we will have, so along y-axis. This y-axis is again your bulk material. This is your bulk material. This is very important point. So again, your bulk material. So again, you will have Schrodinger's equation as d2 psi by dy2 plus 2m by h cross square of E of psi is equal to 0. So this is your problem, and you can solve this problem, and what you will have from the first equation, you will have kx square, and for the second equation, you will have ky square. And if you rightly remember the problems that we have solved, the value of this kx and ky, when we use the boundary conditions, what we obtain is that this kx is n pi by L, and this ky is also n pi by L. So kx and ky are given as n pi by L, and I'm interested in the ground state, so n is equal to 1 will give me kx equal to pi by L and pi by L. Now, if I go back to my argument that since we are talking about k has the reciprocal relations with the length, and here we are having two dimensions. One is along x, another is along y. So you are in two-dimensional plane. If you are in two-dimensional plane, you immediately talk about the Brillouin zones. So your Brillouin zone boundary for n is equal to 1 will be kx giving us pi by L, and for ky equal to pi by L. So what do I expect? Now, if I think about k, what is k? K square is kx square plus ky square. Now, because this k is a vector, so we can have the magnitude of k, because your particles, your electrons are in the framework of two dimensions. They are in a framework of x and y. So k square is kx square plus ky square. So if I merge the two equations, and what is my k square then? The k square should be 2m by h cross square E. This should be the case. So from this equation, I can calculate the energy of the electrons. I am not calculating the energy of electron along the z direction. I am calculating the energy of this electron along x and y. And x and y are in finite dimensions. These are very, very long dimensions. The electrons will never see the edge of the x. They will never see the edge of y, but definitely they will see the edge along the z-axis. That's the most important point. So E will be h cross square by 2m times k square. So E, energy, you can see the symmetry of this energy will be kx square plus ky square. Now, what does this equation tell us geometrically? The equation tells us geometrically that you will have your allowed energy levels will have a circular geometry. So this circular geometry, which is basically the consequence, which is basically these Brillouin zones, this circle will have an area. And the lowest possible area of this circle is pi by L whole square. This pi by L. This is the lowest possible area within the framework of that circle. So if I want to calculate the number of energy levels, the number of allowed energy levels, assuming my problem to be in the framework of very, very low temperature. So what would I get here? I would get here number of energy levels. Number of energy levels. Energy levels, I mean allowed energy levels. The allowed energy levels. So if I assume that to be equal to n, this n will be simply the area that I have. The area is pi r squared. You have a circle, and the largest area that the circle will have will be pi r squared, and r will be reflected by k. So pi k squared divided by the smallest possible area. The smallest possible area will be pi by l whole squared. And this thing has to be multiplied by 1 by 2. Now, this 1 by 2 is the result of the distribution of electrons in this two-dimensional system in the framework of, with the source of Pauli's exclusion principle. So we can see here n. So I can calculate this n, and you can see this pi k squared by 2 pi squared times L squared. So this will be my n for the time being. But I have already calculated k squared. And what is k squared? K squared is, what's k squared? It's 2m by h cross square e. 2m by h cross square e. So I can use for k squared 2m by h cross square e. Okay, this is my k squared. I have used for k squared. Then this pi will cancel with the square. So I'll be left with L squared by 2 pi. So here I will have times L squared by 2 pi, and this is my number of allowed energy levels. Alright, that's fine. So n is, so I think this 2 and 2 is going to cancel. Now this m, as I already told you, this m is basically the effective mass of the electrons. So I'm not putting a star on it. It will again act as a constant in my problem, so it's not going to change the direction of my physics. So n will be n L squared by h bar squared e. And what was our target? Our target was density of states in this two-dimensional plane, because the confinement of electrons is only along the z direction. They are not confined in a plane of x and y. And what we have done, we have calculated the number of allowed energy levels as n. Once we have calculated the number of allowed energy levels n, we can calculate the density of states. Now, what is density of states? Density of states. Density of states. That is d of E. And what is that? That is dN by dE. Number of allowed energy levels per unit energy range can be a crude definition of density of states. So we can calculate the density of states from this equation. So what will be that? That will be d by dE of, for n, what we have, for n we have ml squared This should be pi also. ml squared by pi h cross squared. ml squared by pi h cross squared E. So this will give me the density of states. If you rightly remember the photograph that I showed you, the graph that I showed you for the density of states, it was a step-like graph. And why was it like that? Because you will see the differentiation of energy with respect to the energy will lead us to 1. So you will see the density of the states is independent of the energy. It's not proportional to the energy, as we saw when we were talking about the Sommerfield's model for three-dimensional box. So what we are seeing here is this B of E is a constant. And what's that constant? It is ml squared. It is ml squared by pi h bar squared. So this is why you have independence of the energy. So this is why you could see the step-like situation for density of states. For every transition of the energy, you have a constant density of states. I think this was our density of states in that photograph. So this is density of states along x and y. Now, talking about the total energy of the electrons. Now you see what we have. We're in the framework of a nanomaterial, and this is a quantum well, and we know what's a quantum well, and we understand that a quantum well has 2 macroscopic dimensions, and the third dimension is a nano dimension. Now I want to write down the total energy of the electrons in this quantum well. So what that total energy will lead us to. That's the point. So what we have x, we have y, and we have z. X, y, and we have z. This is macroscopic, this is macroscopic, and this is nano. So what we will have total energy as the energy along the nanoscale, the energy in the quantum confinement. If you remember that technologically designed quantum well, taking 2 wide bandgap semiconducting stripes and putting a very, very thin layer of a low band semiconductor. That leads to what's called as a quantum well. So you will have total energy will be the summation of E nano plus E bulk. So E bulk we have calculated, and I think E nano is already calculated because E nano is your particle in one-dimensional box. You have a scale from your scale for your electron will see the boundary when it's confined along the z, but this electron will never see the boundary when it is moving along x and y. This is the difference between the two. So for E nano, so if I have to write down the total energy, for E nano I will have the same thing. N square pi square h bar square by 2ml square. These are your energy eigenvalues. You will have quantized energies of these electrons in z direction. Plus E bulk. Now what is E bulk? We have calculated that. If I rightly remember, it was h cross square by 2m times kx square plus ky square. So you can realize that you have a continuous form of energy when you think about this problem in terms of x and y. But you have the quantized states of energy when you think about the same system along the z direction. So this equation will lead us to the total energy of this quantum well. So I hope I tried my level best. I hope you love it. I hope you like it. So goodbye and have a nice time.